like sometimes you do updates, right? And then when you do updates, like it might mess up some stuff. So what we do is that we can rebuild like the entire, like we can clump up the entire thing like after square root q of the updates. Actually, this is quite hard to explain without the problem. So we can move to the problem. So this problem is first query is we paint a blue node to red. So this is just one direction. You won't paint a red node to blue. And then the second one is calculate which red node is closest to the vertex that is specified in the query. Yeah, so we just calculate the shortest path from a red from any red vertex to a given vertex. So actually this problem can also be solved in central decom, which can also solve like if you change from red to blue and blue to red. But we will do the easier square root solution. So the idea behind this is that like let's consider like a naive brute force solution. What we can do is that after each query, for each blue for each red vertex.
Sorry, don't have the drawing app
Oh,
open.
I did it again. Why do I keep forgetting? So what you can do is that for each query, this is the query vertex, then this is red. So if there are a bunch of red vertices, what we can do is that we loop through each of the red vertex and then we calculate the distance between them. This can be done using LCA. So for each query, we just loop through every single red vertex and see and calculate the distance, and then we take the maximum among them. So this will take q times n log n time, because there can be at most n red vertex. Okay, then now let us consider a different algorithm that is also slow. So what we can do is that after whenever you update a vertex to red, you can do a DFS on the entire tree. And then you update that, oh, this vertex is 1 away, 2 away, 2 away, 2 away, 3 away, 3 away. And after that, like when you have a new red vertex, right, you update with like the new maximum. Is maximum, right? Wait, no, it's minimum. Yeah, so for when you have a new update, then you update with the minimum. So this is 0, 1, 2, this is 1. Then if you have like a new one again, let's say this one, then you need to update again this 0, this 1, this 1, this 2, this 3. Yeah, so this is also slow OQN, because after each update we have to do a DFS. So we can actually sort of combine these two solutions together. So the idea behind it is that for the first few queries, right, we got R, right? We use the first method. So we just do LCA to find LCA, LCA. Okay, then after square root q queries, right, which mean that there are square root q r vertices, we do the second method. So the second method, right, is like we update like the distance array. So like this distance array, right, is actually like multi-source shortest path. So multi-source shortest path is basically like normally when we do shortest path, right, we do BFS. Then when we do BFS, we just push the source node inside the queue, and after we do BFS. But since now we have multiple rate nodes, right, that means we have multiple sources. We push all of them into the BFS queue at once, and all of them has distance 0. Then after that, we do the BFS. So we update all of these have distance 1, then all of these have distance 2. Yeah, this is all 1, this all 2, this 3. Yeah, something like that. Then after you do this multi-source BFS, right, we can delete all the rate nodes here because we have already considered them. So now we start back at 0 rate nodes. So like for the next square root q, right, so that means from square root q to 2 square root q, right, we can do the same thing again, like we take the LCA, but at the same time we need to take the maximum with the distance array also. So this means that like if we keep doing this, right, this means that after each square root q update, we do multi-source BFF to reset rate nodes. So this means that the method 1, right, method 1 will only have at most square root n rate nodes. So square root q rate nodes. So this means that this is q square root q times log n. Then for method 2, right, method 2 is just BFS, so it's just n. But since we have to do this after each of the square root q updates, this means that q over square root q times we need to do the update. So this is just n square q. Yeah, so this is solved. Is there any question? To explain, so I'll just briefly go through like the main idea. So elephants is like a combination of the buckets trick plus the rebuild trick. So for elephants, right, basically you have a bunch of elephants on the number line, and then you also have like a camera that can cover like a range, and you want all the elephants to be inside at least a single camera. So like you can have multiple cameras at different position to like capture different elephants. But the hard part of the problem is that there will be updates where you change the position of the elephant. Like first you come up with a greedy observation that like if you have an elephant at the leftmost point, it's obviously optimal to start the camera at the leftmost point, and then you just have the elephant inside. Then we have a next elephant that's out of range, then you do the same thing. So like this idea is somewhat similar to like the first question that we covered, which is holes. So like the first question that we covered, like we have like the jumping thing, right? So like in the same way, right, we bucket the array first. So if we bucket the array, right, like in the same way, like what we store like is that in each element, right, like if we like do this greedy algorithm, what's the first point that like it goes out of range? If it goes out of range, right, then we need to continue from the next bucket. So this means that in like just looking at a single bucket, you can jump to the next bucket already. So you only need like O n over b jumps. The hard part is updating, because when you update, right, you change the position. So let's say like at first, like let's say the bucket size is 3 lah, then you have 3 here. Then what if suddenly you update the position and it goes all the way to the front? Then now this place got, this one got 4 okay, wait, let's make it even uglier. Like let's say it goes somewhere in the middle here. So now this bucket has like, one bucket has 4, one bucket has 2. So like this changing of position like messes up everything, because if we keep shifting, right, like even though at the start we only have square n, if we keep shifting everything over, then like it's possible that the entire array is like in a single bucket. So the way to resolve this is that it's the same thing as what we did. After each square root q updates, we reset the whole thing. So this means that like let's say at the start it's possible to have like square n. Okay, let's just make everything n to make it nicer. So square n updates. So it's possible that after the update, right, like let's say like everything, each of the square n update all put here. So this it like this, the array size can go, the bucket size can go to up to 2 times square n. But after that, right, if you reset everything, right, this means that like we break up the bucket all over again. So we like remove all the bucket, and then we just look through the array as it work, like as a original array, and then we just make a new bucket. So in the new bucket, everything is back to square n. Yeah, so if we do this after every square n update, right, this means that the bucket size will never exceed 2 times square n. And after that, to reconstruct the buckets, you can do in O(n) time by like a linear scan. So this means that since we each n over square n time, right, we need to do a linear scan in n times to reconstruct the bucket. So this is n square n, and then like plus like the query and stuff, like since it doesn't exceed 2 times square n also, so it's also like q square n, something like that. Yeah, so this is the main idea behind this problem. Are there any questions? Okay, the last part is Mohs algorithm. So this Mohs algorithm is an algorithm that can be used to solve offline problems. So the key point for Moh is that it has to be offline. And then after that, normally for Moh problem, right, like there are like a bunch of queries, and then each query is like L, R. And then in order for you to use Moh for this kind of problem, like one property that you have to do is like, let's say you need to maintain the answer for L to R. Then you need to know how to progress from this to, if it is from let's say you know the answer from L to R. If you are able to progress from L to R to L, R plus 1, and you can also move from L to R to L plus 1 R, and also L minus 1 R. So if you can do this quickly, right, like from a range of L to R, you can find the answer to L from L to R plus 1, and then like these three ranges, right? You can find it like in O1 time, right? Then after that, then you can solve in O Q square root n time or something like that. Q square Q square n. I don't know which one it is. So the big idea behind this is that we want to reorder the way that we solve the queries. So what we can do is that we have buckets again. So each bucket is of size B. And then after that, we have a bunch of queries, right, with Li, Ri. We want to sort them in such an order such that when you go from Ri to Li plus 1, Ri plus 1, you want to use like as few of like these three operations as possible. Like because if we can do the operation in O1 time, if we can do like very few of those operations, then like our time complexity will be small as well. So in order to do that, right, what we can do is that we sort the queries based on which bucket the left endpoint is in. Then if they belong to the same left endpoint, we sort by increasing right endpoint. So the reason why we do this is that because let's suppose like all of the queries like the left endpoint is in the same bucket. So this is the second case where I say if they belong to the same bucket, we sort by increasing right endpoint. So this means that the query will be like something like that. Like let's say this is the first query, this is the second query, then after this is the third query, fourth query, fifth query. Yeah, so the thing is that like since the left endpoint is only inside the bucket, right? This means that the left endpoint moves by at most b times each query. Then for the right endpoint, right? Since the right endpoint is increasing, this means that for a single bucket, right, the right endpoint can just keep going right. So this means that the right endpoint only this means that right endpoint moves by at most n in a bucket. So it doesn't matter how many queries are in the bucket. There can be like many queries inside the same bucket, like the left endpoint are in the same bucket. But the right endpoint will always move by at most n. So what this means is that as we move on, right? So like what I said just now, right? We sort like based on the the bucket of the left endpoint first. So when we move to a new bucket, right? We can use the same argument again. So this means that for the left endpoint moves by at most b for each query. This means that we use q times b operations. Then after that, the right endpoint moves by at most n in a bucket. And then since there are n over b bucket, right? So this means that this n over b times m. So if we calculate out, this is qb plus n square over b. So if we assume that n and b are roughly equal, right? So it's like nb plus n square over b. So if we let b equals to square n, we get n square n plus n square n is O n square n. Yeah, so with this idea, right, we can solve like this type of range query problems easily. So let's take a look at the example problem. So static range inversion query. So you just want to print the number of inversion from L to R. So in a normal like if we want to find the inversion, right, what we do is that we keep a family tree, a binary index tree. So if we want to find the inversion, right, let's say like 3, 1, 4, 1, 5. If we want to store the inversion, right, we store like a binary index tree. Then we store that 3 occurs once. Then we have 1, we want to see like how many elements are smaller than 1. No, how many elements are more than 1. So since this is 1, that means the answer plus 1, right? And the contribution increases again. Then for 4, we see how many stuff is more than 4, and this plus 0. Then for 1 again, now is it strictly more than? Yeah, strictly more than. So this one we check this one, then this plus 1 again. Then for 5 is plus 0. So each time we want to check like how many stuff is more than it, because of the condition that like the number of inversion is the number of I comma j, where I is smaller than j and bi more than bj. So since we are, if we process from left to right, that means each time we are looking at j, then we want to find all the bi more than bj. So we take a range sum of all the stuff that is bigger than bj. So now, right, since we have this kind of range query, we can actually see that it is quite easy to progress from R to R. Then we want to progress to L plus 1 to R plus, or something like that. So what we can do is that when we have a range, right, we store the binary index tree, the number of occurrence. So let's say 1 occurred 2 times, 2 occurred 3 times, 3 occurred 0 times, 4 occurred 1 time, 5 occurred 3 times. Then when you want to decrease the range, right, you need to remember like how much contribution AL did. So the number of contribution that AL did is, we look back to the formula. If for all i's more than j, bi more than bj. So now since we are considering L, right, L is like the smallest in the range, so we are considering I. So we want to look for all the bi more than bj. So let's say AL is like 4. Then after that we want to look for all the bi's more than bj. So this means that the AL contributed like to 5. So you need to decrease the answer by 5. So like in the same way, like if you want to move to like L to R plus 1. So in this case, it's like what we said just now. We just A R plus 1. We want to add AR plus 1, right? Then we need to look for the elements bigger than it. Yeah, so since we use a family tree, right, we incur additional log n factor, but it's still like n squared n log n. Let's see whether. Okay, then we move on to the next question, which is N and books. So for this one, is Okay, so this one is basically you have a bunch of books, and after that you have two types of book. Let's just call it type 1 and type 2 book. And then like there are n bookshops. Each bookshop sells the same type of book, but they can sell like they can sell AI number of book. And then after that, like you want to find like what's the number of consecutive ranges such that the number of type 1 book minus the number of type 2 book is equals to k. And then you want to find the number of possible uh, contiguous segments that there can be that are between L and R. So it's like in the example 1112, right? This means that in bookshop 1 is type 1, bookshop 2 is type 1 book, bookshop 3 is also type 1, and bookshop 4 is type 2. Then each of the bookshop sells only one book. So you have a query like 1, 2, and then k equals 1, which means that you want the difference in the number of type 1 book minus type 2 book is equals to 1. So you have like 1, 2, right? The only possible segment is 1, 1 and 2, 2. Because if you take 1, 1, then you have 1 type 1 book and 0 type 2 book. And then you have to like if there's like 3 book inside the bookshop, you have to buy all 3 books. You cannot just choose half of it. Okay, then the way to solve this problem, right, is that instead of type 1 and type 2, we just if it's type 1, right, then we let it be AI type 2 negative AI. So what we want to solve now is that the sum of the we want to find the number of consecutive segments such that the sum is equal to k. Okay, and then when you want to think of the sum, right, like for this kind of sum problems, the first thing you need to think of is prefix sum. So now we can reduce the problem to count the number of ij such that prefix sum of j minus prefix sum of I minus 1 equals to k, where else
Sorry, but you're not sharing the drawing screen.
yeah. Okay, so what I said just now is that instead of considering type 1 and type 2, we can just change it all to just the number of books that is inside. So type 1 means that there are AI books, type 2 means that there are negative AI. Then the problem becomes you want the sum to be equal to k. So in this kind of problems with sums, we always want to consider the prefix sum. So now the problem becomes count the number of I and j such that the prefix sum of j minus the prefix sum of I minus 1 equals to k, where I smaller than equals to j smaller equals to r. The L and R is each query. So in order to solve this problem, what we can do is that we store like a map. Store a map of prefix sum. So this because like what you can change this to is that p sum j equals to k plus p sum So when you have a new p sum j that you want to add into like the range, right? Like you have from L to R, right? Then we want to do the mole, right? We want to use most algorithm, we need to know how to move to L to R plus 1 and whatever. So in order to move to L to R plus 1, right, this means that we need to consider the contribution of P sum R plus 1. And the only contribution that P sum R plus 1 can contribute to the array is based on this condition. So this means that like you need to find let me change this. So it becomes minus k. So this means that we want to count the number of I where p sum I minus 1 goes to p sum r plus 1 minus k, where I is in this range. So in order to count this I, right, we store the number of I where specify this condition inside the map. So you can just add on like that contribution into the answer, and after at the same time you update the map. Yeah, and then in the same way when you decrease to like L plus 1R, right? For this case, it's also very similar. That we just count the number of I, and then instead of adding, we subtract from the answer. Does it make sense? Are there any questions? Okay, if there are no questions, let us move on to the last part. Okay, so for the last question, right? Basically, you have a graph. Then in the graph, the queries are like if you have the queries are given L to R, right? If you connect all the edges between like each edge is numbered from 1 to m. And then if you are given like L to R, where L to R are like the edge number, and if you connect all the edge between like the edge, all the edge where the edge number is between L to R, right? How many connected components are there? So this is like a DSU question, right? Because we want to count the number of connected components. But the problem is that like we have the L to R condition. So like if we want to do more, like let us recall what the condition is. We need to be able to move from L to R plus 1. This one is easy because we can just do
Sorry, can you share the screen?
yes. How many times have I forgotten? Okay, so like I said earlier, if you want to go from L to R to L to R plus 1, this one is easy because we can just do a join inside our in our DSU. Then from L minus 1 to R, we can also use join. The hard part is when you have L plus 1R. And because in DSU, we cannot delete edges. So how do we handle this? So like if you have heard of DSU rollback, you might be thinking, oh, actually DSU can sort of do deletion because we can roll back. But actually this doesn't work because if you recall inside our our query, right? Like sometimes we move the left, sometimes we do the right, sometimes we move the left, sometimes we move the right. But in our rollback, we can only like undo our last action. So if we do the right after that, right, then we want to roll back the left. We cannot actually do this. We have to roll back everything here first, then we can roll back this. So rollback doesn't work. But what we can do instead is that we can modify our mole algorithm. So if you recall inside our mole's algorithm, in our mole algorithm, our left endpoint always go like inside this bucket only. Then our right endpoint always goes right. So if you think about it, right, like maybe we can just like ignore the left endpoint first. So what we do is that our DSU, we don't care about the left endpoint. So if we have a query, let's say like that, right, we join the edges outside of the bucket first. After you join the bucket stuff outside the bucket, right, then after that only you join the stuff inside the bucket. Then after that you already have like the DSU one. Then after this query, right, like we don't want to care about the bucket anymore, so we just do the rollback. Then after that we in the next query we continue to move the right endpoint, right. Then after that in the same way we do the left endpoint again. So like let's say the query is something like that, right? So we move the right endpoint already, then after that we move the left endpoint. After we move the left endpoint, then we move it back again. Then after that we continue moving the right endpoint. Then we can move the left endpoint again, then after we move back again. So this actually still works because the left endpoint still moves at most b time. Actually this time is 2b, but like in time complexity analysis it's still OB. Yeah, so this algorithm will still work. So the time complexity is like n square n log n, because for rollback we need to incur an additional log. So are there any questions? Okay, if there are no questions, then that is the end. I'll end here. Goodbye.